Color. On a chilly autumn day, colors are everywhere. Deep reds, bright oranges, soft yellows, and light greens. Color is an interesting phenomenon of light. It allows us to differentiate between otherwise identical objects. Our eyes show us the world as it is, they don't deceive us. But what about the places our eyes can't show us? These are the cosmic cliffs, one of the James Webb Space Telescope's first images. The cosmic cliffs offer a stunning view of a stellar nursery within the Carina Nebula. When gazing at this surreal depiction, one may wonder, is this what it actually looks like? As you may know, Webb sees infrared light, which we cannot. Neil deGrasse Tyson argues that these colors in this image are real. He claims that these colors are authentic and legit. I have to disagree.
Are these colors enhanced at all by NASA, or is this what the telescope is seeing?
Okay, you want to go there? We'll go there. So in your eye, you have red, green, and blue, RGB sensors in your retina. What we define as visible light is the light that comes through and is detected by these three. You can't see infrared.
Okay.
But what the telescope does is it can take images in 3 different bands, separate bands of the infrared. Then you hand it an RGB and create a color picture, which is the color you would see if your eyes could see infrared. So it's authentic and legit.
Before I became an astrophotographer, I thought of space differently. When I looked at a Hubble image of some galaxy or nebula, I saw some distant place that had no link to the world I knew. It existed merely in the void of space. However, that is simply not true. Every one of those deep space objects isn't in a faraway void of space. They're above us in the sky. Arguably, the most iconic image ever taken of space is this picture, taken by the Hubble Space Telescope. Dubbed the Pillars of Creation, these nebulous pillars of gas and dust reside within the larger Eagle Nebula. A nebula is simply a cloud of gas and dust in interstellar space. The Eagle Nebula is an emission nebula composed of ionized gases emitting light of varying wavelengths. 90% of emission nebulae are hydrogen, with the rest being helium, oxygen, nitrogen, and other trace elements. Every element on the periodic table has a unique property known as its emission spectrum. This spectrum is composed of various wavelengths of light that an atom of the specified element will emit when one of its electrons transitions from a higher energy state to a lower energy state. Narrowband imaging captures one specific wavelength, a wavelength emitted by an element of interest, by using special filters. The most common narrowband filters used for astroimaging are hydrogen alpha, oxygen 3, and sulfur 2. I'll now be referring to these as HA, O3, and S2. HA and O3 are of interest because emission nebulae contain large amounts of hydrogen and oxygen. S2 is of interest because sulfur is often present near active regions of space, such as massive stars and supernovae. A huge advantage of narrowband imaging is that every other wavelength of light, including unwanted light pollution and moonlight, does not get to the sensor, so only the light from the nebula is being imaged. By only examining these 3 elements that make up the nebula, its structure can be observed more easily. Since the moon is out tonight, it's the perfect opportunity to image the Eagle Nebula in narrowband. Between the telescope and the camera is a filter wheel containing an HA, an O3, and an S2 filter. Now, let's take another look at the Eagle Nebula, this time through narrowband filters. Okay, the first HA photo just came in and it is magnificent. You can clearly see the pillars right there. Each filter shows the composition of a different gas within the nebula, each with its own intricate details. Previously, this light was hidden beneath the rest of the light, but the filters have singled these wavelengths out. At this point, I have data on 3 separate bands of light, HA, O3, and S2. These bands of light don't quite correspond to the red, green, and blue wavelengths that our eyes see. Hubble's picture of the Eagle Nebula uses something called the Hubble palette, which maps the emissions of S2 to red, HA to green, and O3 to blue. Now, in reality, HA is not green, nor O3 blue. However, this allows the different gases to be easily visualized. So I'm on the computer now, and I'll go ahead and open the images. Here's the HA. Here's the S2 image. And here's the O3 image. So, the O3 image, there's not too much oxygen in the nebula, but you can see the pillars outlined still. If we look at the sulfur data, there's a little bit more sulfur in the nebula. A few more details are kind of defined here, and you can see the pillars still. And then let's take a look at the HA. You can clearly see there's tons of hydrogen. The majority of this nebula is hydrogen. So you can see the shape of the eagle here, kind of the wingspan, the head up here. Then you got the pillars of creation in the center. So since most of the data here is concentrated in the HA, whichever color channel gets assigned HA is going to be overwhelmed by that color. So if I go ahead and combine these here, let's do the Hubble palette first. So we're going to assign red to sulfur, green to HA, and blue to O3. So if I go ahead and combine those, here is our new image. So this is the raw image when you assign sulfur to red, hydrogen to green, and O3 to blue. You can see that the image is dominated by green, which is hydrogen. So another way to do this is if I assign hydrogen to red, which is truer to its natural color. Hydrogen is 656 nanometers, which falls in the red category. So if I do red to HA, green to S2, and blue to O3 again, if I combine these, now we can see that the image is mostly red because hydrogen has been mapped to red. This image would be a more accurate representation of the data because hydrogen itself is actually red. How about I assign oxygen to red? Let's do sulfur to green and hydrogen to blue. Let's see what that does. Gives it a kind of ghostly appearance, in my opinion. Some of these fainter blue areas are kind of harder to see than they were when it was assigned to red, but you can still see the pillars and the general blue outline of the Eagle Nebula. Let's try S2 to red, O3 to green, and HA to blue again. It's pretty similar to what it was before, with the hydrogen still being assigned to blue. However, there's a bit more of a purplish hue on the outside here, which is likely due to the S2, which is red. So the red and the blue are kind of mixing here to make a purplish color, which is the hydrogen and the sulfur that are mixing here. So this is a different way of doing it. It's a variation on the Hubble palette, but instead of assigning each filter to a different channel, I'm kind of mixing them around. So the red is getting assigned 0.6 times S2 plus 0.4 times HA. The green is gets a little bit of all of it, and the blue is still O3. So this produces a more golden image, which is often seen in Hubble's images. So now it's kind of a soft golden color. This is one of my favorite ways to arrange the colors, along with the HSO, which is the straight up red combination. So let's go take a look at the final products I've produced. I did one where I took the HSO, which was hydrogen to red, which you can clearly see by the abundance of the red hydrogen here. So this is just like the end product after further processing to bring out the details and such. And then I did another one, this time using the modified SHO palette, and this is the goldenish version. So between the two, I think I like this one better, even though the red one is technically more accurate since the hydrogen is represented by the color red, which in the real world it is also red. This picture isn't quite true to reality, but it is still a valid representation of the data here. So that was kind of an overview of the different ways that I can combine the 3 filters into RGB color space to represent each of these elements with a different color and to turn this monochrome data into a nice looking color image. So as you saw, there are a myriad of different ways to represent the light of HA03ANS2, and this is the one that I think I have settled on. It's my favorite. You might disagree, but this is my personal preference. This is why every picture of space, including mine, is fake. By taking the light from each of these elements and assigning them to either red, green, or blue, the element no longer represents its true color. The light emitted from the hydrogen gas within the nebula was red, so my eyes would see it as red. However, in the picture, the hydrogen no longer appears red. This applies to any combination of narrowband filters handed into the RGB color space, including the bands of infrared light that the James Webb Space Telescope used in the picture of the cosmic cliffs. This is my final product, which was made with 5-minute exposures through narrowband filters and handed into the Hubble palette. I disagree with Neil deGrasse Tyson when he says that these pictures are authentic and legit, because the wavelengths of light that this image has assigned to red, green, and blue are not consistent with how our eyes perceive those wavelengths. However, these pictures are not meaningless. They are still representations of real data that has been translated into a way our minds can understand. Color serves as a tool to differentiate otherwise identical objects, and these pictures are simply taking advantage of that fact. Plus, who doesn't like admiring the beautiful colors in these images?